We're getting there. I know this is a ton. It's a ton, but this is will be the last video or two as far as information goes. Spinning room and conical pendulum examples. These are also typical amusement park rides. Spinning room. There's an amusement park ride where riders stand against a rough wall on a cylindrical room. The room spins faster and faster. Once the room is spinning fast enough, the floor drops out and floor drops out from under everyone, but friction keeps the riders from sliding down the wall and falling. It's a crazy experience if you've never been on it before. Suppose a rider's mass is m, the radius is r. Coefficient of static friction between the wall and the rider is mu. What is the minimum angular speed that must be achieved before the floor can drop out? What would your first step be? Right. Free body diagram, because we're talking about friction. And friction is a force. Whenever we're dealing with forces, we go to a free body diagram and then Newton's second law equation. Weight still points down. This time friction will point up because friction opposes sliding. Friction is always parallel to the surface, and friction is what prevents this person from falling and sliding down. Also, the normal force is pointing towards the center because the normal force is always perpendicular to the surface, and this surface is vertical. So the acceleration this time is going to point towards the center of the room because we're going in a circle like this. So if we're going in a circle like this, then the acceleration has to be directed towards the center of that circle. So we have balance forces in the vertical because the person's not sliding, right? And it's perpendicular to the acceleration. So there's no acceleration in this way. We also have a net force that is just the normal force. We're moving in a circle, so the net force is the centripetal force. The only force pointing towards the center of the circle in this instance is our normal force. So the stuff that makes it go minus the stuff that holds it back is normal force minus nothing. So we can just say normal force equals mass times our centripetal acceleration. This problem mentioned angular velocity. So we're not going to use v squared over r like we do most of the time. Instead, this time we're going to use that other centripetal acceleration equation, which is omega squared times r for the centripetal acceleration. So mass times centripetal acceleration. That's all this means. If the room barely spins fast enough to keep the person from falling and the static friction is at its maximum, then our frictional force, mu Fn, right, maximum, then Fn equals m omega squared times r, and Ff equals mg. We can plug these in to get frictional force equals mu times Fn, and get frictional force equals mu times Fn. Cancel out these m's and solve for the speed that can barely get the person around the circle without falling. So looking at this relationship, we have omega, and then we have coefficient of friction in the denominator and radius in the denominator. So what happens if you increase the radius here? Make this bigger, then the speed can drop, can get smaller. Meanwhile, if the coefficient of friction is smaller, then you've got to spin faster, right? Less friction, so you've got to create more revolutions per second to allow for a greater normal force, so your frictional force will go up. This is also shown by the fact that mu is in the denominator, so smaller mu means that this has to be bigger. If the room has a smaller radius, we already talked about this, then the person has less linear speed. By the equation, v equals omega times r. Less linear speed means the person has less normal force, less friction, and will then fall. So a smaller radius room must be compensated by having a faster rotation. And the equation shows that with r in the denominator. So whenever you're analyzing, well, what would happen if I make this variable larger or smaller, and it's within that square root within the radical, just forget about the radical, and just look at, okay, this is in the denominator. So if I'm keeping this, if I wanted to keep this the same, but if I change this, what's actually going to happen over here, you can analyze that. And this is an important skill in physics. So it allows us to look at these relationships and make predictions about what will happen before ever making any changes.